Okay, so welcome back to another video. So in today's video we have an infinite series, the infinite series from -1 quantity to the power n, multiplied by sine of n, and then divided by n cubed. So here we have a trig function, and then multiply with -1 to the power n, which you'll see that's kind of like an alternating series, and then just divide by that with the reciprocal of the cubes. So it's not going to be too crazy. We're actually going to be using some complex analysis to evaluate this series and then manipulate some stuff as we go through. It's not going to be anything so like convoluted or crazy, but anyway, let's just jump right in. So I'm going to define our function in terms of theta. So f of theta is equal to our infinite series, -1 quantity to the power n multiplied by sine of n theta divided by n. Okay, and now one thing I would like to note is that sine theta, if we use our definition of Euler's formula, we know that sine theta is actually just equal to the imaginary part of our exponential e to the power I times theta. So we're going to use this substitution to replace this, but however, we have n times theta as our input, so rather this is going to equal to, so let's see, rewrite our infinite series again. And then this is -1 to the power n multiplied by the imaginary of e to the power I times n times theta, then divided by n. However, I can actually move the imaginary part outside, so I'm actually just taking the imaginary part of this infinite series. So we have that this is the imaginary of our infinite series, let's see, -1 to the power n, and I can actually factor out the exponent of n, so we get that this is just e to the power I times theta, and then to the power n, then divided by n. So let's use a little fact here. We can actually use the following Taylor series. So note that the negative natural log of 1 plus x, don't worry, it will be replaced with our function u. We'll call this u equals e to the power I theta. So just note that the Taylor series expansion is the following. So this is the infinite series of -1 quantity to the power n multiplied by x to the power n, and then divided by n. I'll put this equals over here just to show that this is the same. So we see that this is actually just equal to the negative natural log of 1 plus e to the power I times theta. Okay, I'll write this better. I'll put a little, like, kind of looks like a sideways if and only if kind of depiction. So that's how it's defined. So that means so far we have that f theta, really it should be the imaginary of this, but again I'm going to write this out. So this is the equal to the imaginary of negative ln of 1 plus e to the I theta. So now we're going to do something here, and that is we're actually going to expand the complex logarithm. So I'll state that we know that 1 plus e to the pi hour 1 plus e to the power I times theta, we know that that's a complex number. I'll just denote the complex number system. So that means we want to use the we're going to expand, like I said, we're going to expand the complex logarithm. So that's what we're going to do. So that means so let's actually work this tool out. So we have that the natural log of z. So z is our complex numbers, simply our standard x plus so x plus I times y. And then really x plus y can be represented in a form of the polar series. This is equal to r multiplied by e to the power I theta, r being the radius, meaning we're actually taking the modulus of our complex number. Simply it's just square root of x squared plus y squared. So I'll write it this way. x squared plus y squared. And then we're actually finding our, have to find our explicit formula for theta. Simply, if you were to graph this in a complex plane, you'll see that this is actually just the inverse tangent of y divided by x. Okay, good. So we have that, so we can actually rewrite some things over here. So really, using natural logs, we have that this is natural log of x. Well, really, actually, let's substitute the x plus I times line with its polar form. So ln of r times e to the power I theta, okay? And then using natural log rules, we can actually separate it into the addition of two natural logs. So this is the natural log of r multiplied or plus the natural log of e to the I theta. Let's see, so this means rewriting this a little further, we get that this is the natural log of, I'll replace my r with the square roots of x squared plus y squared. And then ln of e just cancels, and then the exponent I times theta is simply just moved in front of the natural log. So we get that this is simply just I times theta. And then if we rewrite this a bit, we actually get that this is just 1/2 multiplied by the natural log of x squared plus y squared. And then plus I times our theta, which is the inverse tangent. I'm just gonna write arctangent this time instead of y divided by x. We have that 1 plus e to the I theta. Actually, let me put this a little further. We know that if we expand this out using Euler's formula, we get that this is the same thing as 1 plus cosine theta plus I times sine theta. Okay, so if we were to equate this, our complex number, to here, we can see that the real number, or the real part x, is simply just equals to 1 plus cosine theta. So we can just put everything in x back to here. And then sine theta, which is the imaginary part, is that equates to our complex y. Okay, good. This means if we were to take the imaginary part of this negative natural log of 1 plus e I theta, then basically the only thing we only have to concentrate on is just the arctangent. So going back to the red, so far, the imaginary of the negative natural log of 1 plus e to the I theta, okay, and that's simply just equal to, so the imaginary is just arctan of y divided by x. Now if I were to input back our y, what we equate the complex number from here, this is actually just arctan of, let's see, that's supposed to be sine theta, and then divided by 1 plus cosine theta. Okay, cool. Now, we're actually going to do something a little different to continue further. This is actually supposed to be the negative right here, so negative and then negative. Okay, nice. What we're actually going to do is we're actually going to use the Weierstrass substitution. In other words, this is actually known as the half angle substitution method. So simply, okay, let me write this out first. So Weierstrass, his last name is actually very very difficult for me to remember how to spell. So Weierstrass sub. So we're actually going to use that sine theta is simply equal to 2t divided by 1 plus t squared. Cosine theta is equal to 1 minus t squared divided by 1 plus t squared, with t is actually equal to tangent theta divided by 2. And we actually substitute everything back. So we replace sine theta and cosine theta with everything in terms of, well, it's still going to get theta since we plug t back into here, but let's actually simplify this out a little bit. So we have that sine theta is equal to 1 plus cosine theta, and that's actually equal to, so let's see, 2t divided by 1 plus t squared, then that's divided by 1 minus t squared divided by 1 plus t squared. Okay, if we do some further simplification coming from, actually this is supposed to be plus 1 from that denominator, so let's see, 1 plus 1 minus t squared, then divided by 1 plus t squared. Okay, good. Now, like I said, let's actually further simplify this from the denominator. So 1 plus t squared. So let's see, we get that this is, if we get a common denominator, this should be 1 plus t squared. So this is 1 plus t squared, and then plus 1 minus t squared. Okay, we continue further, we get that this is just 2t divided by 1 plus t squared. That's just coming from here. And then I'll just flip the reciprocal. So this will be 1 plus t squared. And then we cancel out some terms here. Let's see, we get 1 plus 1 is 2. And then t squared minus t squared is 0. So it's just 2. Then we notice that bottom of 1 plus t squared and the top, they cancel. Then the 2 cancel. And so we're just left with just t, and where we set that t is equal to tangent theta squared. So that means overall, arctangent of sine theta divided by 1 plus cosine theta is simply just going to equal to the arc, or negative, forgot to put that down, that's negative. So negative arctan of tangent theta square, or theta divided by 2, the arctangent and tangent cancels, and so you're left with just negative theta over 2. Okay, and so let's reiterate back. Then that means f of theta, which is equal to our sum, our infinite sum coming from what we defined over here. See, infinite n equals 1, then the alternating, see, sine of n theta, then divided by n, which is just equal to negative theta squared, or negative theta divided by 2. I'll put below with, well, not with, but for, such that 0 is less than or equal to theta, which is less than equal to 2 pi. So now, let's actually integrate this twice. You'll see why I did this twice. So that's actually the name of a girl band, but that's not what I'm talking about. Girl pop band as well. Let's integrate this twice. So this means I'll get that we're actually going to integrate using double integral. So this is actually going to be from 0 to t, and then this is going to be from 0 to x of our sum, our infinite sum over here. Let's see, negative 1 n, then sine n theta divided by n. And this is integrating from d theta dx. And then we set this equal to the double integral over here with the same bounds of negative theta over 2 d theta dx. Let's actually first integrate this side. So I'll move this down below. So we integrate this, this means we get, so first double integral, let's see, we have our first, and then we integrate our series in respect to theta. Since negative 1 to the power n and n is just a constant, I'll just move that outside. Or rather, I don't have to really necessarily keep it outside, but like really we just have to focus on integrating sine of n theta, which if you want to check yourself, you'll see that you'll get that this is the infinite series. So n is equal to 1 of negative 1 to the power n plus 1. Since you integrate this, you get a negative 1, and then that actually just goes with the base over here. So you just add 1 to the exponent, which is just cosine of n theta. And then this time you're using the u substitution. So if you do this, you're actually supposed to get an n on the denominator a second time as well. And then this is going from 0 to x, and then d theta, or this is dx. Oops. Okay, so that means continuing forward, I'll get that this is, evaluate our bounds, we get that this is going to be from the integral from 0 to t of our infinite series, n is equal to 1. Let's see, I'll plug x. So let's see, this is negative 1 to the power n plus 1 cosine of, let's see, this is n times x, then divided by n square. And then what I can do is I can actually factor out a negative 1 from here. So this way, this will transform this negative into a positive over here. So we get negative 1, then n, and then divided by n squared, and then dx. Simply because if we plug 0 for theta, we're just going to get that this is actually just going to equal 1 for no matter what values of n you choose. Okay, so this means when we integrate this, then we're going to get that this is the infinite series again. See, n is equal to 1. Then, okay, and then we get negative 1 then to the power n plus 1, then we're just left back with sine of nx, and then divided by n cubed, since you're just doing the same method again a second time. Then integrate this. This is just a constant, so that's not that difficult to show. And n squared, then x, and then we evaluate this from 0 to t. Okay, and then when we evaluate this, I'm actually going to rearrange some terms here. So this means I'll move this first. So we have this is negative 1 to the power n divided by n squared times t. And then factor out the negative from here, and then that will actually change to, this will become a minus this time. And then we're left with the same thing, so negative n, then sine of n times t, then divided by n cubed. Okay, well, actually, this is supposed to be a sum, so give me 1 second to rewrite this. We have that this actually equates to this double integral. Now we just have to evaluate this double integral, but that's actually really easy to show. So let me actually evaluate this in orange. I think I can evaluate this double integral on this side over here. So I'll write this in orange. So let's see, this is 0, t, and let's see, this is negative. So we evaluate this, so we get that this is negative 1 over 4 theta square. Evaluate this from x to 0, then dx. Then we keep going further, so we get that this is 0t. Evaluate this at x. This is just negative 1 over 4 x squared dx. And simply because you just plug 0, you're just going to get 0. Keep going further, you get that this is negative 1 over 12 x cubed. Evaluate this from 0 to t, and then you get that this is just negative 1 divided by 12 multiplied by t cubed. Okay, good. So now let's actually equate everything back to each other. So let's see, I'm just gonna draw this arrow. Let me first write this. Yeah, this should be good. So we actually have the following. So we have these two equations here. Okay, so far we evaluated these two double integrals, and we come to the conclusion that we have this infinite series that is equal to negative to this function, negative 1 over 12, multiplied by t cubed. So now what I'll do is we're trying to achieve our following sum over here, which is actually coming together in a way. So how about this? How about I add the 1 over 12 t cubed to the left hand side and add the negative 1 to the power n sine of nt divided by n cubed to the other side, so we get the following. Okay, so we have the following, and I just factor out the t outside since this sum here only depends on our indexes of n. Okay, now let's actually recall a little definition here. This is a little function known as the Dirichlet eta function, and it's actually defined as the following. So actually over here. So eta of some input s is equal to our infinite series of negative 1 quantity n plus 1 and then divided by n to the power s. So we can actually rewrite this a little bit. This is simply just factor out the -1, so I get that this is just negative our infinite sum of -1 to the power n and then divided by n to the power s. And then another definition, well, it's the same definition really, but let's actually say that for later. Let me first do some substitution. Okay, so I'll replace our series here. This is actually evaluated at when s is equal to 2. So this is the Dirichlet eta of 2. So over here, this is 1 over 12 t cubed plus t times our eta evaluated at 2, and then set that equal to the infinite series from the right hand side, just like that. Okay, now the next thing I want to write is that this is also equal to the following explicit formula. So this is defined as 1 minus 2 to the power 1 minus s, and then multiply by our Riemann zeta function defined at s. Okay, so with that we can actually evaluate some stuff here. So when we do this, I get that so this is 1 over 12 t cubed, then plus t, then multiply by our evaluated Dirichlet eta at 2. So we replace s is equal to 2. We get that this is 1 minus, let's see, 2, and then to the power 1 minus 2. So that's -1. 2 to the -1 is 1/2. So 1 minus 1/2, 1/2. So it's 1/2 multiplied by the Riemann zeta of 2. But we know that Riemann zeta of 2 is basically Basel's problem, which equates to just pi square divided by 12. So let me actually equate this out. So this is 1 over 12 t cubed, then plus pi squared times t, and then divided by 12. And then simply it's just equal to our right hand side of the infinite expression. Now we're down to just the final step. So if you pay attention, if we were to plug t is equal to 1, we're actually it actually equates to the exact given series that we're being asked to evaluate. So this means when t is equal to 1, I evaluate t equals to 1 over here. So when t is equal to 1, then it's just 1 over 12 multiplied by 1 cubed plus pi squared multiplied by 1 divided by 12. Simplify this out, we get that this is just, I actually made a little tiny mistake. There's actually supposed to be a minus over here, since simply because I just factored this out. So this is a minus, 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 and then over here is a minus. Yes, and now everything will come together. So minus, minus. Okay. And then therefore, we simplify some things out. We get that this is just 1 minus pi squared divided by 12. And there you have it. That's our final conclusion, drawn in this orange box. Like so. All right, that's pretty cool if you ask me.